Lesson 24, Exponential Functions in the Real World. In the last lesson, we started learning about exponential functions. And remember, those are functions where the x is in an exponent. And an example would be something like y equals 2 to the x power. Turns out exponential functions are really useful in real-world situations. And so I'm going to show you a few examples of how exponential functions are used in this lesson. One area where exponential functions are very helpful is in representing the growth of a population, like the population of a country. Turns out the growth rate of a population usually depends on the population size. And that makes sense if you think about it, because the more people there are in a country, the more babies are going to be born each year. But an exponential function represents this kind of growth really, really well. And that's because an exponential function is set up so that the growth rate of the function is linked to the size of the function itself. So, for instance, when the function doubles in size, the rate of growth of the function doubles. When the function triples, when the value of y triples, the rate of growth of the function triples. That's the way it works. And that's exactly the kind of function that you need to represent population growth, because a population that's twice as big should have about twice the growth rate. And a population that's 3 times as big should have about 3 times the growth rate. And so what we're going to do is let's look at an actual example. It's a fictional example, but we're going to use a country called Bula Bula, and we're going to represent the growth rate of the population of Bula Bula with an exponential function. And since we're going to look at how the population of this country changes over time, we want the independent variable to be time in years. And so we're going to use the letter t to represent that. And then for the dependent variable, we want that to be the size of the population. We'll use the letter p. And we're going to track Bula Bula's population starting from 2007. And so 2007 will be times 0, where t equals 0. And let's say that the population of Bula Bula in 2007 is 12 million people. And so 12 million should be the value of p, the dependent variable, when t is equal to 0. Now, based on these facts and what we learned about exponential functions in the last lesson, it's kind of tempting to write a function something like this, maybe, to represent the situation. P equals 2 to the t power. And then t is time in years and p is population. The problem is this isn't going to work for a couple of reasons. First of all, if we put 0 in for t in this function, then that gives us p equals 2 to the 0, or 1, which says that the population of Bula Bula in 2007, remember 2007 is the year when t equals 0, says the population of Bula Bula in 2007 is 1 person living in the country, and that's not what we want. Remember, the population in 2007 is 12 million. And so this function's not going to work the way we've got it written now. And one change that we can make, let's go back, put the t back up in the exponent. One change that we can make that will fix the initial population and make it 12 million is we can put a coefficient here in front of 2 to the t. And that changes the function of p equals 12 million times 2 to the t. And then this makes more sense, because now when we put 0 in for t, 2 to the 0 still equals 1, but then we are supposed to multiply the 1 by 12 million, and then we end up getting 12 million is equal to p whenever t is 0. And that's what we want. But this function right here still isn't exactly right, because this base of 2 is actually too big. Remember from the last lesson, when you have a base of 2, what that means is that the function doubles every year. And so that would be extremely rapid growth for a country. If a country were growing that fast, then it would end up being the biggest country in the world in no time. See, in this very next year after 2007, we would put 2008 would be t equals 1, and then the population would go up to 24 million. Because you would have 2 times 12 million, which is 24 million. So that's way too fast for the growth of a country. A more typical growth rate for a country would be maybe something like 3% growth per year. Now, to change this function to make the growth rate 3%, it's actually a little bit tricky. What we have to do is change the base of 2 to a base of 1.03, and I'm going to explain where that comes from in a second. See, this is the base that we need in order to get 3% growth, and if we wanted a growth rate of 4%, what we would do is change the base to 1.04. And you see the pattern here. If we wanted a 5% growth rate, then we would need a base in the function of 1.05. Basically, the way it works is the base needs to be 1 plus whatever growth rate you want, and then you just need to write the growth rate as a decimal. So 3% is 0.03, 4% is 0.04, and then you just take 1 plus that, and that becomes the base. Now let me see if I can explain to you why the base has to always be 1 plus the growth rate. It's kind of interesting to see why this works. Let's say that we do want the population of Bula Bula to grow 3% per year. In 2007, the population is going to be 12 million. But then in 2008, the population has to be 12 million plus 3% of 12 million. That's the way 3% growth works. See, here's the original 12 million people that lived in Bula Bula in 2007, and then this is how many babies were born. Or it doesn't have to be babies, it could be people moving into the country, but we just take 3% of 12 million, and then you know how to do that. You just multiply 12 million by 0.03, and then we add that number to the original 12 million, and that gives us the population of the country in 2008. Now, we can simplify this expression on the right, or we can factor it by reverse distributing, because we have two terms here, and then both of them have a factor 12 million, and we can just take 12 million outside parentheses to get 12 million times the quantity 1 plus 0.03. See, this expression is the same as the original, because if we distributed the 12 million times 1 is 12 million, and then 12 million times 0.03 gives us this, and then those two are added together. Now let's figure out what the population of Bula Bula should be in 2009. Here's the population in 2008, and for 2009, what we're going to do is we're going to take this population here, and we're going to add to that 3% of this. That's the way 3% growth works. So it'll be this quantity plus this quantity times 0.03. And this is kind of messy, but you can see what's going on. See, here's the 2008 population, and then we've added to that 2008 population times 0.03. And we can factor the right side again. This time it's a little bit harder to see how to factor it, but there's a factor 12 million times the quantity 1 plus 0.03 in each of these terms. Just think of 12 million times 1 plus 0.03 as the letter A. If we use A to represent that, then the right side looks like this, A plus A times 0.03. See, this is A, and then so is this, and then we've got 0.03 multiplied by it. And we can factor this by taking an A outside parentheses to get this. And so that's what I'm going to do, only A is just going to be this big messy expression right here. And when we do that factoring step, here's what we end up with. 12 million times 1 plus 0.03 times 1 plus 0.03. And then we can write this as a square. And this expression represents the population of the country in 2009. And you may be figuring out what we're doing here. This function is starting to look more and more like the exponential function that we've constructed. Now, look back up here to the function, the expression for the population in 2008. We have 12 million times 1 plus 0.03, and then we could put a first power on this. And then the population in 2009 is 12 million times 1 plus 0.03 to the second power. And then following this pattern, the population in 2010 is going to be 12 million times 1 plus 0.03 to the third power. And then continuing the pattern in 2011, the population is going to be 12 million times 1 plus 0.03 to the fourth power. And so the way it works is that the exponent is always the year, t. And that's how we end up with something that looks like this. And all we did here was just add the 1 and the 0.03 to get 1.03. That's where this comes from. That's why the growth rate is 1 plus, or the base rather, is 1 plus the growth rate. If you play around with this function, you'll see that it works exactly like it's supposed to. If t is 0, then 1.03 to the 0 power is just equal to 1, and then 1 times 12 million is 12 million. So you get a population in time equals 0, which is 2007, of 12 million. And then if t is equal to 1, then that makes this equal to 1.03, and then to get the population, you take 1.03 times 12 million. That's going to give us a population that's 3% more than 12 million, which is actually 12,360,000. And we could graph this function on a coordinate plane. It has the same basic shape as the exponential functions that we looked at in the last lesson. Now, obviously, we've had to adjust the scale on the y-axis. This is y equals 12 million, and this is the y-intercept. One thing to notice is, remember in the last lesson we talked about how exponential functions have a y-intercept of 0, 1, and this function has y-intercept of 0, 12 million. The 0, 1 is the y-intercept whenever the coefficient right here is 1. And that's true of the simplest kinds of exponential function, because when you put 0 in for t, then this power is going to equal 1, and then there's no coefficient here. But when you have a coefficient, then the y-intercept is going to be 0, and then the y-coordinate will be whatever that coefficient is, which makes sense because, see, this is the value of the function at time equals 0. That's the starting out point. And this particular function allows us to represent 3% growth rate, the 3% growth rate, but we can use the same kind of function for different size populations and different growth rates. We can adjust this. That's what's so useful about exponential functions. They'll apply to lots and lots of different situations. The starting population is going to be always the population when t is equal to 0. And you know, whenever we put 0 in here, this whole thing, this power is equal to 1, and then p is just going to be equal to whatever the coefficient is. And so really, this number right here is always going to be the starting population. And so we can just create a more general formula. Instead of having a specific number here, we'll just put a letter in here. And we usually use P0. And the 0 is not an exponent. It just means that this is the population at time equals 0. So this is more general population. This function here only works whenever the starting population is 12 million, but you can put anything you want in for the starting population here. And then to change the growth rate, what we do is we change this part right here, this 0.03. This is the same as 1 plus 0.03. And then if we wanted a growth rate of, instead of 3%, let's say maybe 17%, then we would change this to 1 plus 0.17. Or if we wanted an 11% growth rate, we would change it to 1 plus 0.11. And so this number right here is always the growth rate that you want written as a decimal, and it's usually shown in the general formula, it's shown as the letter R. And so we can use this formula to set up any exponential function to represent a growing population. No matter what the population size is initially, we just put that in here for P0, and no matter what growth rate we want to use, we just put that growth rate in for R, and then we have a specific function to model a certain population. And actually, this formula can be used to represent more than just population growth. It can represent anything that is growing exponentially. And technically, something is growing exponentially when the growth rate depends on the size of the function itself. And that just means when the function doubles in size, when p, the dependent variable, doubles in size, the growth rate is going to double. When the function triples in size, the growth rate is going to triple. That's how you know you have something which is growing exponentially. That's what this phrase means. Now, in everyday life, people will a lot of times say that something is growing exponentially when they really just mean that it's growing fast. And it's probably because they just don't know a lot about math and they don't understand the technical definition of exponential growth. And they'll say that something's growing exponentially, but there are a lot of things that grow fast that don't have exponential growth. For instance, we could have a function that looks like this. Y equals x to the 6th. This is really rapid growth. As x goes up, y is going to go up really fast because you're always going to raise the x value to the 6th power. That's really growing fast. But it's not exponential growth because the growth rate doesn't depend on the value of the function itself. But you'll hear this term a lot in everyday conversation. Now, we talked in the last lesson about exponential functions that have a base that's a fraction, that's between 0 and 1. And these also qualify as exponential functions. And then we looked at a couple of examples. Here's one of them. F of x equals 1/2 to the x power. And remember, any exponential function with a base like this between 0 and 1, the function actually goes down as x increases. And just to show you, here's the graph of 1/2 to the x again. And see, it's just getting smaller and smaller, the value of y is, as x heads toward positive infinity. And this kind of exponential function is actually called exponential decay, because the function is getting smaller as x increases, so it's decay. It's the opposite of exponential growth. And actually, in an exponentially decaying function, the growth rate is negative. So it's really a rate of decline rather than a rate of growth. But the important thing is the function's value and the growth rate or the decline rate, those are still linked together. And that's why it still qualifies as an exponential function. Basically, the way it works for an exponential decay function is when the function's value is cut in half, the rate of decline will be cut in half. Or if the value of the function went down by 10%, the rate of decline would go down by 10%. The rate and the function's value are linked. Turns out there are a lot of real-world uses for exponentially decaying functions, just like there are for exponential growth functions. Just to show you one quick example, when a doctor gives a patient a drug medication, there is quite a bit of the medication in the patient's bloodstream initially. But then the amount of the medication in the bloodstream declines over time. Well, it turns out the decline can be represented by an exponential decay function. So here's our specific example. Let's say that a doctor is giving a patient 5 milligrams of a particular drug and expects the amount of the drug in the patient's bloodstream to decrease by 33% each hour. And we need to write a function to represent the relationship between the number of milligrams in the patient's bloodstream and the time since the drug was given. This is a classic situation for an exponentially decaying function. And the reason is the rate of decrease, see, is a percent of the amount of the drug in the patient's bloodstream. The rate of decline is linked to the value of the function itself. And what we can do here is we'll let m be the number of milligrams of the medication in the patient's bloodstream, and then we'll have t be the number of hours after the drug was first given. And then what we want to do is set up the function using the basic form that we learned about for exponential functions. But instead of using p equals p0 plus r, or 1 plus r to the t, we're just going to change the letters since we're having m represent the number of milligrams. M is the dependent variable, and then the initial number of milligrams is going to be m0. It's really just the same function, different letters. And then remember from the problem, the number of milligrams given to the patient initially was 5 milligrams, and so we want to put 5 in for m0. And then the rate of growth is actually negative. We want to put rate of growth in for r. It's negative. It's going down 33% each hour. T is the number of hours. And so what we want to do is put in negative 33% for r, but then we have to write it as a decimal. So we want to put in negative 0.33. And then here's what's kind of interesting. If we simplify this base by adding these two, 1 plus negative 0.33, then the base turns out to be 0.67, which is less than 1. It's a fraction. It's written as a decimal, but you could write it as a fraction. It's a fraction between 0 and 1, which is an exponential decay function. See, you could think about that's what causes, one way to think about exponential decay function is what causes the base to be between 0 and 1 is that the growth rate is negative. So you have 1 plus a growth rate, but with a negative growth rate, that then makes the base turn out to be less than 1. But this is the function representing our problem. And then we can use this to figure out how many milligrams of the drug are in the patient's bloodstream after a certain number of hours. Let's figure out how many milligrams there are in the bloodstream after 3 hours. To do that, we just need to put 3 in for t. And then we need to calculate the matching value for m. I'm going to use a calculator on this. I'll just put in 0.67, and then we want to raise that to the third power, so I'm going to press the exponent key, and then 3, and then enter. And so this is the value of the power, and then now I can multiply that by 5 times 5, and then press enter again, and we get 1.50 something. And I could have punched it in by just pressing 5 first. I could have done 5 times 0.67, and then the exponent key, and then raise that to the third power because the calculator does understand the rules for the order of operations. I could have done it just from left to right, but you can do it the way I did it too. Either way will work. But we end up with M equals a little bit more than 1.5, which means the amount of the drug in the patient's bloodstream after 3 hours is a little over 1.5 milligrams.